A novel rounding and truncation-based approximate multiplier for reducing the number of partial products. Abstract: in this paper, we present an approximate multiplier in which operands are scaled with truncation and rounding parameters, and multiplication is performed by shift, add, and small fixed-width multiplication operations, ensuring large improvements in the energy consumption and area occupation related to those of the original multiplier approach. The scalability depends on the truncation and rounding parameters, which can be varied as per the requirement. By implementing the truncation and rounding parameters, the levels in obtaining final result can be reduced compared to that of exact multiplier schemes. Enhancement of this work is done by improving the accuracy of the proposed multiplier. The proposed work is designed using VHDL, simulated with Modelsim, and synthesized using Xilinx ISE Design Suite 14.2 tool. Keywords: truncation, rounding, approximate, VHDL, partial products, accuracy, absolute error, energy, scalable. Introduction. In considering the deep submicron technology, power has become a main concern due to increase in transistor count, higher speed of operation, and greater device leakage currents. Scaling in nanometer technologies created problems in reliability and testing. So deep submicron technology has much leaned towards power. Commercial success of products depends on size, speed, weight, cost, computing power, and battery life. Many DSP applications involve complex probabilistic mathematical models and are designed to process information that typically contains noise. So, for some computational error, they exhibit elegant degradation instead of catastrophic failure. Multipliers are one of the data path operators which occupy major share in a digital system. So, hence a multiplier is one of the deciding factor for system's performance. In addition, these multipliers consume most of the area. Hence, optimization of area and speed of a multiplier is a major design issue. Approximate computing is a paradigm where we can reduce energy consumption or boost up the speed, or at times both. By using the approximation techniques in multiplier techniques, one can have the advantage of low energy consumption or high speed. As these computations result in approximate results which are very near with the exact computation, these are best choice for the applications which are error resilient. Most of the recent trending technologies like machine learning, computer vision, and image processing are some of the areas where applications are designed to deal with noisy inputs and generate satisfactory results, as shown in Fig 1. Venkata, Narayana, Assistant Professor, Department of Electronics and Communication Engineering, JNTU Kakinada, India. In several cases the best usable algorithms cannot acquire exact results every time. Occasionally it is besides expense to produce optimal results when dealing meta-heuristics and probabilistic algorithms. Insofar, the designers have largely adopted a notion of exact numerical or Boolean equivalence between the implementation and specification at different layers in the hardware and software stacks. Approximate computing focuses at multiple layers of the hardware/software stacks to trade off computation accuracy with performance, power, and or area. The Table 1 presents the types of approximations wherein the schemes can be applied to various levels of the stack to achieve desired outcomes. In this work we mainly rely on the data approximation, as the input data will be truncated to small widths and the shift unit logic is altered with logic 1 to observe reduced absolute error. The multiplier is used mainly in respective DSP applications and contributes in intensifying the performance of the practical application. This work includes the implementing both truncation and rounding schemes on input operands and produce the approximate results in minimum number of steps in which they are very near to the exact multiplication approach. Additionally, calculating the absolute error for 8-bit, 16-bit, and 32-bit of the proposed multiplier scheme in accordance with exact result, and enhance the absolute error by modifying the least significant part of the multiplication process. Selective approximation analysis of software code or instructions to suggest a certain accuracy mode for a part of code. Timing relaxation, relaxing of synchronization, timing, and handshaking constraints to reduce control overhead. Functional approximation, an approximate alternative of an algorithm that improves area/power performance. Domain-specific approximation, leveraging the domain-specific knowledge for approximations in applications and their algorithms. Data approximations, use of unreliable memories, load value approximation, data truncation, data decimation, etc. Table 1. Categorization for the types of approximation. In general, the process of multiplication involves partial products generation from the acquired operands and cumulate those partial products to a level till 2 rows are persisted. Now by employing an adder the remained rows adds up to generate final result. The process of approximation can be carried out in any levels of the multiplication process. One can use approximation in the beginning of the process, i.e. on the operands, to reduce the partial products number for a multiplier. The process of approximation can be applied at accumulation of partial product to reduce the power consumption. By employing an approximate adder at the ultimate step of adding, we can achieve betterment in power consumed by a multiplier. In this paper, we introduce an approximation method for reduced number of partial products by considering truncation and rounding parameters, which are denoted by T and R respectively. Previous methods of approximation techniques involves employing either truncation or rounding parameters. In this work, by considering both the parameters, we can achieve better outcomes than former methods. Let A and B be two 16-bit operands. Multiplication of A and B results 256 partial products. Hence, by processing all the 256 partial products, we get the result, and it occupies large area. So to reduce the partial products, we employ scalable truncation and rounding parameters as per the requirement. Let us consider the truncation parameter T equals 7 and rounding parameter R equals 3 as illustrated in the figure 2. The green square represents the 1 in the equation, 5, and the orange circles denotes the partial products of approximation, and the blue triangles denotes the truncated bits of input operands. The remaining gray triangles of the operands and the gray circles of the partial products can be neglected. With truncation and rounding parameters mentioned in figure 2, only 31 partial products are required to produce approximate result, which is very close with exact. Around 87.8% of the partial products were reduced. This reduction of partial products will increase with increase in bit length of operands. 2. Hardware implementation. Block diagram implementation of the proposed signed approximate multiplier is shown in figure 3, which comprises of following units: approximate absolute unit, AAU, which produces inverted results if the input is negative and is not changed if input is positive. For unsigned multipliers, this AAU can be eliminated. Leading 1 detector unit, LOD, will provide the leading 1-bit position in the most significant part of the operands. The position of the LOD can be obtained by using KI equals II40 equals I equals N2, 1, only one bit of the signal K is 1, which says about the position of the leading bit. For both operands A and B there exists leading bits Ka and Kb respectively. Truncation unit, 2, deals with truncating the approximation inputs based on leading 1 position and converts into fixed width operands. Arithmetic unit, O, will implement the addition of truncated fixed width operand along with product of approximated input with unity, which can be expressed as 2 equals 1 plus, yay, T plus, YB, T plus, yay, APX times, YB, APX, 2, shift unit, so, shifts the resultant of arithmetic unit with Ka plus KB times leftwards to generate the result. Sign and zero detector unit, SZD, produces the sign of the output based on the input operands of the multiplier. SZD will produce 0 if any of the input is 0. In case of unsigned multiplication, this unit is replaced by zero detector unit. Numerical example of proposed multiplier. Fig 4. Example for 16-bit approximate multiplier. The approximate result, A times B, APX equals 2890136. Whereas the exact multiplication result, A times B, exact equals 291900802. The approximate results are very close to the actual results. 3. Absolute error calculation. To measure the accuracy of the proposed approximate multiplier, we use a parameter named absolute error, which is specified as shown below. Absolute error, AE, equals, PAP P, /P, 3, PAP denotes approximate value and P denotes exact value. Percentage of absolute error can be calculated as percentage of AE equals, PAP P, /P * 100, 4. In considering the calculation of 16-bit multiplier in above section, the percentage of absolute error is calculated to be 0.99% of the actual result, which is very low. For results and comparisons. In the proposed work, the shift unit of the absolute multiplier is modified with logic 1 instead of logic 0, and the observations are as follows. A equals 11,761, B equals 2,482. Exact result equals 11761 times 2482 equals 291900802. Approximate result with logic 0 in shift unit equals 2890136. Approximate result with logic 1 in shift unit equals 289669111. Hence, by intensifying the shift unit, the absolute error has cut down from 289,426 to 223,891. Fig 6. Simulation of 16-bit absolute multiplier with intensified shift unit. Fig 5. RTL schematic of proposed absolute multiplier. V. Conclusion. The proposed approximate multiplier in this paper is designed by considering the rounding parameter r equals 3 and truncation parameter t equals 7. By altering the logic of shift unit, the error rate is reduced from 0.99% to 0.76% of the actual result for 16-bit multiplier. Acknowledgement. I wish to record my obligation and gratefulness to all those who helped me to prepare this paper. I want to convey my thanks to my guide Mr. E. Venkata Narayana, Assistant Professor in Department of Electronics and Communication Engineering, for his valuable advice and guidance towards this work. I received motivation, encouragement, and hold up from him during the course of work.